what we just left off with was one of the problems that we are faced with when we have more than one variable to bring into the equation. We can expand that. That was just one example. We can expand this to what we call the subset regression problem. So when we, very often, what we do with a study is, so we have all these babies, you know, you're gonna measure everything you can measure, because the cost, so there's the cost on the parents, there's the cost on the baby being measured and all that. That, you know, you want to make sure that you've extracted as much information as you can. There's all these other costs, of course, of setting up your study and all that. But so what you're doing when you're investigating is making sure that you're measuring everything. But then you know that all these things, everything under the sun, is interrelated with each other. And so that's not what you're looking for. You're looking to see, is there a parsimonious way of explaining what's going on in terms of the more important, most important variables. And this we can generically label, or umbrella if you will, as the subset regression problem. So you've got an outcome variable here, in this case head circumference, and then you've got a whole bunch of variables that you can use to explain this. Which ones do you use, in what combinations, etc. That's called the subset regression problem. Now, there are a couple of things, three things that one can do for the subset regression problem. What we can do is we can do all possible models under the sun. So if there are q variables, then we can do all 2 to the q, turns out it's 2 to the q model fits. Now, apart from the fact that if you've got thousands of observations and q is sizable, it's going to take you the rest of your life to do all this. Tycho Brahe did this, that's okay. And he came up with some wonderful empirical rules. But anyway, that is problem number one. We also have the huge problem of the Bonferroni problem, if you will, of related tests. And we're going to try and disassociate these things and find out what is truly happening and what's not happening. So it's a very big problem, and it's a very difficult problem to solve. But here's one way to do it. Do all possible models and then look at your R-squared in each one, or look at your T's or something like that, and then compare models to each other. So that's one way to proceed. Not advisable, but it's one way to do it. I mean, we could entertain such a thought today because the computers are cheaper and they're faster and all that sort of stuff. Another approach is what is called a forward selection. And what you do is you choose one variable. Somehow, you choose one variable, then push that into the model, and then look at all other variables that you can bring in. What's the next best variable to bring in? So what you can do is all their single regressions, one at a time, look at the one that gives you the best R-squared, or look at the one that gives you the highest, smallest p, or something like that, and then select variables in that direction. That's called the forward selection procedure. Then there's also what is called the backward selection. And what you do is you fit all you fit all the variables in one shot, you just fit them all, and then kick them out. One by one, kick them out. And drop out the least significant, and then move on to the next one. So redo it. So find the least significant, kick it out, then redo it, kick out the least significant, redo it, and so on. Okay, so here are three approaches that you can take. And there are some computer programs that have been automated to do all this. I would strongly recommend that you don't use any of these. They're problematic, and so this problem hasn't been solved anyway to an extent where we can program these things and have them do it for us. Okay, the problem is that mathematically you're not going to get the same answer in these three. You know, you can have all three available on your computer, and you're not going to get the same answer when chances are when you do all three approaches. And one of the problems is that you run into what is called collinearity. Two things are collinear. The most extreme case is you might have somebody's weight measured in kilograms, all right? And that's one variable. Then you might have the same thing measured in pounds, and that's the other variable. And the two are the same variable, basically, because you can transform the one to get to the other. In other words, they are collinear, okay? They are perfectly correlated with each other. Well, it turns out that not only would you run into problems when you have that, but you would also, even if you're close to that, if they're not perfectly linearly related to each other, but they are closely correlated to each other. So if you have a high correlation, you might run into interpretation problems and fitting problems. And that's the collinear problem. And I believe that that's what the problem we just ran into when we looked at toxemia. If you look at the model, and you looked at the model for toxemia, if you looked at the coefficient, when you have no interaction term in the model, the coefficient was minus 1.412. It doubled in the model when you brought in the interaction term. And the tip-off, you say to me, well, what's the tip-off? The important tip-off, what has tipped me off in my practice when I've run into this before, is you look at the standard error. Look at the standard errors. There's a 10-fold increase in the standard error. And that's usually a tip-off that you've got some multicollinearity, possibly. So, and look at the t-statistic. The t-statistic went from significant to quite insignificant. By adding one term, you shouldn't be seeing this big a difference, unless it's very highly related to before. And look at the p-value went from 0.001 to 0.574. And the R-squared didn't change. The R-squares didn't change at all. They were basically the same thing. Tip-off that you've got multicollinearity. And in this case, it makes a lot of sense because, as I said before, toxemia happens later in the pregnancy. And later means gestational age is higher. So was it the higher gestational age, or was it the toxemia that's feeding you the same thing gestational age was? And so then what is toxemia? And then what is the interaction term? So they're highly related with each other. So that would be the problem. So be careful when, as I said, in this course we can't go into all of these situations. I'm just giving you the tip of the iceberg here. It's a fascinating iceberg, and I hope you continue your studies in this area. But right now, that's it. That's where we're going to leave it. So be careful of multicollinearity.